All right, welcome to another IAEI News Live. My name's Thomas Dimitrovich, and today's topic is complex variables and the power triangle. And it all starts now. All right, so complex variables. I know this is going to be a math-intensive hour for us today. I want you to understand that. So hopefully you will get a calculator out. You're going to need a calculator. You can use the calculator that's on your phone. I'm going to use my calculator that's on my phone. And it is, I use an HP app. It's RPN Scientific. It's a 42S. And what you'll need is, you'll need the ability to do the trigonometry function, sine and cosine, inverse sine and inverse cosine. And what you'll see is on your app, on your calculator, inverse cosine will be shown possibly as ACOS, A cosine. And inverse sine is A sine, ASIN. So just be mindful of that. I am traveling again. This is a recorded session, unfortunately. But I'm teaching a class and I am on the road again. Sounds like a name of a good song. So I do want to say before we get started, I spent some time at the board meeting for the IAEI. Hopefully, if you are an IAEI member, you were able to tune in to that board meeting. It was quite it was a really great session. We did a strategy session as well. So we're working on the strat plan, the strategy for IAEI. The great news, we're getting some great financials and our membership is doing better than it has ever. We're on the right track. So that's all I got to say about that. And you're going to see some great things coming out of IAEI in the near future. So stay tuned. And if you're not a member of IAEI, I encourage you to get out there and get that application filled out and get in as an IAEI member. There's a lot of resources that are out there for you. And as I said, we're going to continue to grow those resources. So, all right. So let's just first think about complex numbers. Now, complex numbers, just as a fundamental, what we have to understand is that all of our power distribution systems, if you're doing calculations of any magnitude, short circuit current calculations is a great example. You have to understand that all of the components within a power distribution system have an impedance. They may be pure resistive, and they may be pure inductive. They could be pure capacitive, or they can be a mixture of all three of those. To understand the dynamics of a power distribution system, there are some fundamental tools that we use. Complex variables, the power triangle, two of the most fundamental building blocks for any, I'll say, engineer or any qualified person who is embarking on calculations with regard to say short circuit current as an example, power factor correction as another example. So what I want to do in this session, I want to build your foundation around this concept of complex variables and talk a little bit about the power triangle. The power triangle gets us right back to trigonometry, which takes you right back to possibly high school. And we're going to be using trigonometry to solve some very complicated problems. So, before we get to that, I can't get to that yet. Let's do this. Let's just talk about an important thing that we call, important tool that we call the power triangle. So a power triangle is just that. It's a triangle. We have a horizontal axis. We have a vertical axis. And then we have the hypotenuse. It's important to remember that the power triangle is a right angle. And so a lot of rules apply when you get to a triangle that is a right angle. You probably used one of these fundamentals whenever you tried to square something up. I know on a job sites, my uncle and I, we would when we're laying out a foundation or we're laying out a building and we put the stakes in the ground, he would get his string out. He would establish a perimeter, right? So if he was going to say build something that was square, so let's say that he was going to either dig a trench or whatever it was, he would mark it off. We would put a stake here, and we would string a line across. He would put a stake here. I'm sorry. Nope, not there. He would put a stake here. He would put a stake here, and then he would string a line. And then he would do the same thing. He would put one here and string a line that way, and then put one here and string a line that way. So he would string these lines up, and to determine if he was square, he would measure three, say any multiple of 3, any multiple of 4. So this would be 3, and this would be 4, and that would be 5. A 3, 4, 5 triangle. And if you get a 3, 4, 5 triangle and it measures out great, you have a square. You have achieved what you were looking for. So that's the fundamentals of the power of a triangle. Is we use it in mechanical and construction to help us. Now, this was before you had the tools. Today we have electronic tools to do what we used to do in the past by hand, but we use the power of the triangle. Now, how does this relate to electricity? Every component, as I said earlier, every component has an impedance. A conductor has an impedance. A transformer has an impedance. Busway has an impedance. Motors have an impedance. In most cases, I'd say most cases, that impedance is given in a Z. And Z is your hypotenuse. Think about a transformer. And let's say you had, 500 kVA, and you had 4% Z. Both of those numbers can find themselves on the power triangle. Let's look at the impedance, Z. That percent Z, that Z value is right there. And Z is comprised of a resistance, R, and an impedance X. And what we call this up here, because it's on that axis, we call this J. It's just, and J is an imaginary number. I can't believe I'm talking about imaginary numbers on this YouTube channel. And how you would write the coordinates for Z. It's equal to R plus JX. There's your X, and there's your R. So that percent Z can be broken out into a resistance and a capacitance. And they can be represented in the form of a power triangle. In some cases, for transformers, you can, and if you do your homework, transformers have what they'll tell you it's a, so say we're dealing with a transformer, and they'll say that it's 4% Z with an X to R ratio, I don't know, of 3.5, something like that. What does that mean? There's your X, and there's your R. And what they're giving you is the angle. They're telling you how to calculate. They're giving you everything you need to calculate this angle theta, which is your power factor. But they'll give you, by giving you the percent impedance and an X to R ratio, they're giving you enough to calculate R and calculate X of that product. You'll sometimes see the utility give you an available fault current. They'll tell you an X to R ratio. And I want to help you understand what that means, because it all gets back to trigonometry. It is so cool. So let's get back to the triangle again. And I am not good at drawing a right triangle, so I always put that little square down there just to tell you it is a right triangle. Okay, so here's your triangle. We said, remember that transformer? We said it was 500 kVA. Where do you think kVA is on this transformer? kVA is right here. The hypotenuse is VA. And what is kVA comprised of? It's comprised of a real component and a reactive component, or an impedance. So it is resistance and X, impedance. So all of your kVAs, I'm sorry, geez, I'm still stuck on impedance. kVA is power. So we have P for power, and we call it Q for VARs. They always represent VARs as the letter Q. So mind your P's and Q's. That's where it comes from. I highly doubt it, but that's what my story is. So you have over here, let's just take the K out of it for now. We have VA. We have power across the horizontal. That's your real component. VARs up the horizontal or the vertical, and that's your reactive component. And that is your angle. Now, transformers will be published with an X to R ratio. They'll tell you what the X to R ratio is. And that's basically giving you that number so that you can calculate theta. Because we're going to get to the equations for this transformer, but I want you to understand the reality of it, the practical application of what we're going to discuss from a math perspective, because you need to know power factor. Power factor is that angle. We need to understand VARs. Why would I need to know VARs? Because if I want to correct the power factor to make that angle as small as possible, I have to add capacitance in the negative format so I get a resulting angle, possibly something like that. So I've taken my power factor, my theta, my angle, and made it smaller by adding capacitance into the system to correct power factor correction, to correct down to as close to unity as I can get. You want to be probably around 0.95 power factor. This is the practical application of this triangle. I want to, before we get into the math, I want you to at least understand that. So now let's talk about this triangle and basic trigonometry, which you probably learned in high school. So let's say this is R, and this is X, and this is Z. What do we know based upon trig? The equation that we can rely on. I gotta find room. I'm gonna move this a little bit. Just gonna move that over there. So what are our equations? Here are the key equations you need to know. Cosine of theta equals adjacent over hypotenuse, R, that's not right, sine theta. Sine theta is equal to R over Z. Cosine of theta is equal to X over Z. Tangent of theta is equal to X over R. So if I give you theta, or if I give you the angle, if I tell you what your power factor is, or I tell you what your X to R ratio is, if I tell you what the X to R ratio is, I'm telling you what tan of theta is. Then you can calculate the angle theta, and then you can calculate all of these other numbers that are associated with this triangle. These are important equations that you need to understand. So if I want to transpose, so if I say X, I could take this R, I can take this R and move it here and say R times resistance times the tangent of theta is equal to X. I can say Z times the cosine of theta is equal to X. Z times the sine of theta is equal to R. These are important equations, because now I can take this transformer, for example, 500 kVA transformer with a 4% impedance, and if they gave you an X to R ratio, I can calculate the R and the X. So let's just assume, let's do this. I'm going to do something. I know that I let's go back to my power systems classes. Codes and practices. Let's see, events, file, presentations, power systems analysis and design. I've got complex numbers, Ohm's law, no, I don't. Transformers. Let me go to equipment. I think I have it under fundamentals. So there is IEEE documents published have published X to R ratios when you manufacture transformers. So loads and similar equipment. Let me look at loads. I don't know if that loads would not be right. Transformer distribution equipment is what I'm looking for. And I don't know that I have. There it is, distribution equipment. So let's look at transformers. Transformers low voltage. So when you make when you manufacture a transformer, especially the large transformers, they'll publish an X to R ratio. And a lot of those are found, those ratio values are found in IEEE documents. So you could break down those values. So let's just go back while that's loading up. If let's say that my X to R ratio is, say I told you that you have an impedance of 4.75 and an X to R ratio of 3. I'm just making numbers up. What does that mean? That means my Z is 4.75 and my tangent of theta is equal to 3. So if I want to know what the angle is, I say tangent to the -1, or a tangent of 3 is equal to theta, the inverse tangent. 3 inverse tangent, so that's 71 degrees is theta. So if I made it, so for example, if 1 inverse tangent of 1, say it was 0.8, inverse tangent of 0.8. So inverse tangent, if X to R was 0.3, then my inverse tangent would be 38 degrees. But we'll stick with the number 3. Although it's probably not a very realistic number, but it doesn't matter. We're just doing math at this point. So that if I give you an X to R ratio, I am basically telling you what the power factor of the circuit or the piece of equipment or the system is at that point. So now I know 4.75 is Z. So if I draw my triangle, this is 4.75. Because of the X to R ratio, I know this is 71 degrees. I have an R and I have an X. R is equal to 4.75 times sine of 71. 4.75, 71 sine times is equal to 4.49. What is X? X is equal to 4.75 times the cosine. of 71. 4.75, 71 cosine times 1.55. I can square that plus 4.49 squared. So if I take 1.55 and square that, and 4.49 and square that, add those together, take the square root, 4.75. So, and what I just did, I just verified my numbers. Z is equal to r squared plus x squared, the square root of that. So think about this is basic trigonometry. Think about the triangle. Z is equal to the square root of r squared plus x squared. And this is r, and this is x, and this is theta. Theta is equal to r times sine theta So it's just let's just do the cosine theta. So sine theta, sine of theta is equal to r over z. Cosine theta is equal to x over z. And I can calculate the rest of my numbers just from that. So now you say, well, okay, it's all fine and dandy. You have a transformer. Okay, you take a transformer, and we said it was, let's say it's 1500 kVA, and it's 5.75% Z, and it's 4160 to 480. Okay, we know this is the hypotenuse of that triangle. We know this is the hypotenuse of the triangle. And most times what we'll do for transformers, you think about what is a transformer. A transformer is a big hunk of iron. We'll consider that transformer to be just X, no R, because R is very small and more than likely very insignificant when you start to add conductors on the secondary of the transformer. So, and then as you go down through the system, now keep in mind, every component can be represented as a real resistance or a reactance. And I'm not even showing you what I'm drawing. So I have my kVA transformer. I have my 5% impedance, 5.75% impedance, and that's of the transformer. A conductor is going to have an R plus a JX as well. And where do we get that? I'll show you where we get that. We get that from, you go to nfpa.org, and we're going to go to NFPA link. And we're going to sign in using my facial recognition. And we are going to call up, we're going to go to the tables. And what you're going to go to, so look at this right here. This is table 9 of chapter 9, alternating current resistance and reactance for cables. Now this table is called alternating resistance and reactance for 600 volt cables, 3-phase, 60 hertz. And look at what the numbers inside the table. You have ohms per kilometer as the top number, ohms per 1,000 foot as the bottom number. So, I'll make this smaller. If you look at any one of these conductors, you'll see there is a reactance. That's your X. Remember, that's the vertical part. And there is a resistance. And if you keep going over, there's an effective Z with a 0.85 power factor. Now, what is the phase angle? What is the angle? What is theta for a 0.85 power factor? 0.85 power factor is equal to cosine of theta. So cosine to the -1 of 0.85 is equal to theta. And we have to get our handy dandy calculator. So I'm going to say 0.85 A cosine is 31.8 degrees is theta. So what they just gave us in what they're giving you here is they're giving you the Z at a power factor, and they're basically telling you what R and X are. So for any one of these, if it's 2.7, if I'm going to use 2.7 as my Z, so Z is equal to 2.7 at 31.8 degrees. And I'll tell you how we write that. We write that as 2.7 31.8 degrees equals Z. That is the magnitude of Z, and this is the angle. Now, if you want to know what R is, remember what R is. R is equal to this guy, 2.7 times sine of 31.8 degrees. R is equal to 2.7, 31.8 sine times 1.4228. X is equal to 2.7 times the cosine of 31.8 degrees. And that is equal to 2.7 times 31.8 cosine. And that is 2.2947. Just for giggles. So what do we just do? We just drew the triangle. This is 2.2947. 1.4228. This is 1.4228. And if we say Z is equal to the square root of 1.4228 squared plus 2.2947 squared, that should equal 2.7. Let's do the math. This will check our math. So 1.4228, 1.4228 squared, 2.2947, 2.2947 squared. Add those two numbers together, take the square root, 2.7 on the nose. And that angle is 31.8 degrees. And this is 2.7. So now you've calculated the resistance and the reactance, the power factor angle, and the impedance. And that aligns with what is right here as your effective Z at 0.85 power factor. They are providing you enough information for you to draw that triangle. Now, here are some functions for complex variables. Let's say that I had two impedances. The first impedance was 5, resistance R was equal to 5, and X was equal to 12. And the second impedance, R was equal to 3, and X was equal to, 18. I can, I could calculate Z in both of these. So let's just get the numbers, and I can calculate an angle. So what is Z? Z over here is equal to the square root of 5 squared plus 12 squared is equal to 5 squared, 12 squared. Add those two together, square root 13. So this is 13. How about this one? 3 squared is 9. 18 squared. Add those two together, square root. This is 18.25. So Z is, and Z over here is 18.25. What is theta? Theta is inverse tangent of 18 over 3, right? X over R. So 18, 3 divide, inverse tangent. It's 80 degrees. 80, theta is equal to 80.5377. How about this one over here? Theta is equal to inverse tangent of 12 over 5. 12, 5 divide, inverse tangent, 67.38 degrees. Now, let's say that this is a conductor 1 and this is a conductor 2, and they're both in series. So I have conductor 1 and conductor 2, and I want the total Z of that. I need to add two complex numbers. So now we're going to learn how to add complex numbers. The rule is you add the real, and then you add the imaginary or reactive. And this becomes R plus JX. So what is R? 5 and 3. So we have 2. We have 5 plus J 12 plus 3 plus J 18. 3 plus J 18. We want to add those two conductors to get the total impedance. So we add 5 and 3 and we get 8 plus J, what's 18 plus 12? 30. So the total impedance for this is 8 plus J 30. So, and now what we can do is draw our new triangle. So what we've done is we took 5 plus J 12, and then we added 3 plus J 18, and then we'll get a resultant triangle. And what that adds up to is 8 plus j 30. And we can calculate the new theta for those two conductors connected together. What is, remember, tangent of theta is equal to x over r, 30 divided by 8. So if I say tangent -1 of 30 over 8 is equal to theta. So take 30 and 8 divide, inverse tangent, 75.07 degrees is equal to theta. So this is 75 degrees now. That's how we add. So if I had two conductors in series, or if I had two conductors and a transformer in series, I would add the R's and add the X's. And it's the same thing for subtracting. I would subtract the R's and subtract the X's. So if I want to add lengths of conductors, different types, to add impedances in series with each other, where would I use that? I have a transformer, a conductor 1, and a conductor 2. If the transformer is all reactive, and I say I have 0 plus j 5.75, and the conductor 1 is, I don't know, 3 plus j 1.6, and conductor 2 is 3 plus j 1.6. We'll say they're two of the same conductors at the same length. I would just add those up. I'd add that. You get 6. 5.75, 5.75, plus 1.6, plus 1.6 is j 8.95. And that's the total impedance for those components in series. That's the power of, and then how would I use that is to calculate fault current. If that's the impedance, V is equal to IR, and I know the voltage, V over the impedance is current. That's the fundamentals of a fault current calculation right here. So the first rule is when adding conductors, we add the real and we add the reactive. How about multiplying? Complex numbers. How do I multiply complex numbers? Well, you can do it the long way, which I'm not even going to show you the long way because I don't want to waste your time. This is what we do. We convert the polar coordinates. Will you convert the R plus JX into a phasor? Not like Star Trek. But what a phasor is a magnitude at an angle. So let's take this triangle here. See if I can grab it. Copy. And let's paste it here. Paste. Now, if I want to represent so what's Z? Z is equal to the square root of 30 squared plus 8 squared is equal to 30 squared, 8 squared plus square root 31. Let's just double check. 30 squared, 8 squared. squared plus square root 31.05. That's z. Now, I can represent z as a phasor. I can represent z as 31.05 at an angle of 75 degrees. And I'll tell you why it's important that you know how to do that. If you're dividing or multiplying, we're going to focus on multiplying. If I have two phasors, say it's 31.05 at an angle of 75 degrees, and I want to multiply that by another, which is 10 at 75, I don't know, 25 degrees, I would multiply those two numbers together, so that would be 310.5 at an angle, and I add the angles. 75 plus 25 is 100 degrees. I don't have to, it's that simple. But you would not try to, you can't add phasors. You can't add 31.05 at 75 degrees to 10 at 25 degrees, because what you'd have to do is break 31.05 at 75 degrees into an R and an X, break down the 10 at an angle of 25 into an R and an X, add the R's, add the X's, and then you have your new number. Okay, so that's multiplying. So multiplying, first thing you do is convert to a magnitude at an angle, theta. Second, you multiply the magnitudes. And third, you add the angles. That's how you multiply complex numbers. Now we're going to divide complex numbers. How do we do that? I'm going to give you the recipe first. 1, convert to a magnitude at an angle, just like when you're multiplying. The second thing you do is you divide magnitudes. And then the third thing you do is subtract numerator angle minus denominator angle. So, for example, if I want to divide 10 at an angle of 30 by 5 at an angle of 10 is equal to 10 divided by 5 is 2 at an angle of 30 minus 10. 2 at an angle of 20 degrees. That's how you divide. Now, why? Why would I need to know this? Remember, all that we're doing is we're setting us up so that we can do calculations with components like conductors, transformers, motors, to calculate things like fault currents or power factor at any point in the power distribution system. So if I have a transformer and a conductor 1, and I land on a breaker, and I come off of that circuit breaker, and I have a conductor 2, and maybe I go to a load. I don't know. I'll go to another panel. This has 0 plus JX, because there won't be any, we'll assume the resistance is 0. This will have a resistance plus a JX, and this will have a resistance plus a JX. Now, if I wanted to just add those, I can add those up. And I would use the R's and the X's. But what happens if I put a motor in here? When I put a motor in my system to create the impedance diagram, remember, each one of these will have an impedance. So there's my transformer. There's my conductor 1. There's T1, conductor 1, conductor 2. And if I wanted to draw that motor, it would be in parallel. Motor 1. So motor 1 will have 0 plus JX. T1 is 0 plus JX. Conductor 1 is R plus JX. Conductor 2 is R plus JX. If I wanted the equivalent impedance, I have to add the impedance of T1 to C1 to C2, which is just using real and reactive components. But then, to get the combined, and let's say that this is Z1, all of that. To get this Z2, I have to take Z1 times Z of motor, not Z, we'll call it X of motor, divided by Z1 plus X of motor. It's the simple network reductions that we learned in circuit theory. But to be able to do this when they are complex numbers, this will just be an X, this will just be an X. So it'll be 0 plus JX, which would be a magnitude at an angle of 90. And these, I'm sorry, no, wait, Z1. No, Z1 is actually an R plus JX. So I have an R plus JX times an X. I would put this into a phasor, that into a phasor, a magnitude at an angle, multiply the magnitudes, add the angles. For Z1 plus XM, I would add the reals, add the impedances, convert that into a magnitude at an angle. Then I would take the numerator divided by that magnitude of the denominator and subtract the angles. That's how you use complex variables and that power triangle when we're doing calculations. So let's summarize. Let's go back. Let's summarize. Adding complex numbers. You add the R's and Z's. When you're multiplying, you multiply the magnitudes and you add the angles. When you're dividing complex numbers, you are dividing the magnitudes and subtracting the angles. What do you think? And when do we use it? Why complex variables? All components of a power distribution system will have an R and an X. 2, calculate fault currents And 3, calculate power factor. 4, power quality studies. You have to know these fundamentals to perform many different calculations in a power distribution system. It's the power of the triangle. It's the power of complex numbers and complex variables. And it's the power of trigonometry. It's just phenomenal. All right. So that was a 1 hour. Let's see how much I'm gone 55 minutes. So I'll be at an hour discussing complex numbers. Now what we'll do is we will do another session to basically calculate the short circuit current. Well, you know what I'll do? So this is a fundamental building block for all power system engineers. And I say power systems engineer, you don't have to be an electrical engineer, you don't have to be a mechanical engineer. It's for the qualified person who understands how to do calculations. This is one of the tools. Another tool is per unit. So I will do another session to talk about per unit. And once you have complex variables under your belt and the concepts of per unit, we'll take a small one-line diagram, we'll convert the one-line diagram into a per unit impedances, and that will be a session. And then the final session, we will take that same system and we will calculate fault currents at various points in the power system using per unit and using complex variables to get that done. All right. Well, I know we were talking a lot of math today, and this is completely different than what we usually do. I hope you followed along. I hope you take a snapshot of those equations, do some example triangles, take a look at the code book, table 9, chapter 9. Look at the resistances and reactances of conductors. And tell me some of the takeaways you might have. For example, conductors are highly resistive and less impedance, less X. Transformers are much more X and a lot less resistance. Transformers are that way because of the big inductive core. Motors the same way. Why is a motor operates very similar to a transformer? Think about it. If you're a motor, you are energizing a stator, which is creating a field which pulls the rotor. There's no physical connection other than maybe fields, magnetic fields. You're suspending a rotor in air inside of a stator, and the magnetic fields are causing it to turn. You have an air gap. Think about a transformer. Same type of thing is occurring. Coils around an iron core. Motors have a lot more X than R. Transformers have a lot more X than R. Think about a generator. What's a generator? Instead of the field turning the rotor, you have an external mechanical solution turning the rotor, which is then inducing current and voltage in the stator. It's just the reverse of a motor. Highly inductive and not so much resistive. Let this one sink in. Let this one sink in. Do some examples, just some triangles. Take a look go to the back of table 9, grab a conductor, calculate the Z, calculate the R. Well, they give you the R, they give you the X, calculate the Z, and calculate the power factor angle using your cosine thetas, your sine thetas, your tangent thetas. Practice that. And we will expand on this fundamental. Next, we're going to talk about per unit, what it is, why we use it, what it's used for, and some of the basic fundamental equations you'll need to convert impedance values of things like conductors and motors, etc., into per unit values of impedance. We're going to have fun moving forward. So stick with me. Thanks for joining. Thanks for hanging in there for as long as you did. If you got this far, you're a glutton for punishment. All right? And if you know an engineer, share this video with them. Tell them the IAEI wants to help them get their PE license. We're going to go over some fundamentals of engineering. And we'll all learn something. Thanks. Thanks for what you do for electrical safety. Thanks for what you do for the electrical industry. Remember to stay safe and please stay healthy. Until next Tuesday, God bless.